Okay, so let's get started. So now we are glad to have Benjamin Dupont, who is going to be presenting along with Isaac Rennes, a joint work with Philippe Malbos about the completing periodic rewriting system by Gaussian elimination.
Yes, thank you very much. So first of all, I would like to thank the organizers of the workshop for the opportunity to give this talk here. So today, Isaac and I will present, we'll talk about completion of periodic rewriting system by Gaussian elimination, which is, as Samuel said, a joint work with Philippe Malbos. So the outline of the talk will be as follows. In the first part, I will introduce and motivate the need of optimized completion procedure for periodic rewriting systems. And then in the second part, I will introduce the rewriting properties on operas that we will need in the sequel from the sequel of the talk. And then Isaac will speak at his turn, and we'll talk about the completion procedure F4 for the case of non-symmetric operas. And in the last part of the talk, he will illustrate this procedure for the study of the anti-associative opera. Okay. So let me introduce the need for this completion procedure. So first of all, let me state that this work takes place in the context of algebraic rewriting. And algebraic rewriting is a big theory whose objective is to apply some methods from rewriting theory in algebraic contexts. So to do so, one takes a presentation of an algebraic structure by generators and relation, and fixes an orientation of the relation and try to deduce some properties on this algebraic structure using rewriting theory. So for instance, algebraic rewriting can be used to solve decision problems, for instance, with the word problem studied by Tu in 1914. But it can also be used in other extents. So in symbolic, it can be used with symbolic computation methods. So for instance, one can use such rewriting theory to compute homological invariance of an algebraic structure, to compute free resolutions, or to compute cofibrant replacements. And what we will be interested in here today is that it can be used also from algebraic geometry to solve systems of polynomial equations. And how does it work? So this problem of solving polynomial equation using rewriting theory has been developed in the context of elimination theory, which is a theory in mathematics aiming at eliminating variables of polynomial systems in order to be able to solve these systems. For instance, the first principle of elimination theory, I could say, is Gaussian elimination. That is a natural process that arises when you want to solve a system of linear equations. You can use Gaussian elimination, but it turns out that it is more complicated in the case of nonlinear equations. And in that setting, Grobner basis, that I will talk a lot about today, appears as a tool to solve such nonlinear systems. So that computing Grobner basis is an important question to that extent. And actually, that will be the objective of the talk today, to compute a Grobner basis for an operatic rewriting system. And to do so, we will start by a set of polynomials, which will be given by some set of relation of a presentation. And we will try to complete it in order to compute a Grobner basis. And actually, there is a way to talk about Grobner basis in terms of rewriting theory. So rewriting theory appears here because, as I will explain in the next slide, a Grobner basis is only a confluent linear rewriting system that is compatible with monomial order. And so computing a Grobner basis will be equivalent to completing such a linear rewriting system. So let me explain a bit more how now. So to do so, consider a starting point that is X an alphabet, and consider the X star to be the free monoid on X. So in what follows, you can think of X as being some variables and X star as being some words on the elements on X that you may see as monomials. And a condition that we will need to impose throughout this talk is that we have to get an ambient monomial order on our objects, so here on X star. And such a monomial order is a well-founded total order that is stable under the algebraic structure. And here it's stable under multiplication. It means that if U is smaller than V, then we should get that W times U times W prime is smaller than W times V times W prime for any monomials W and W prime. And if we fix such a monomial order, then if we consider a polynomial on the variables of X, it will admit one biggest element with respect to this order, which is called its leading monomial, and that we will denote by Lm of U. And such a monomial, let's say if we write over a field or a ring, admits a leading coefficient in that field or ring that we will denote by Lc of U. And now we can define what is a Grobner basis for an ideal I generated by a set of relations that has to be compatible with the monomer order. And such a Grobner basis is a subset G of I, of this ideal, such that the ideals generated by the leading monomials of both I and G coincide or the same. So this might be a bit abstract yet, but there is a well-known fact in the theory of Grobner basis, which is the following, that G, a subset G of I, is a Grobner basis if and only if the rewriting system arrow underscore G, whose rules are defined like this, is a convergent rewriting system. So let me explain a bit more about how these rules are defined. So these rules, you take a polynomial U in G, and you will choose to reduce the leading monomial of U into this quantity. And if you look at this quantity, this is nothing but the polynomial U in which you removed the leading monomial. So in some way, you take the leading monomial and you rewrite it into the remainder of the polynomial U. And this gives you a set of relation, and the fact that G is a Grobner basis is equivalent for this set of reductions, to be convergent. And that's what we will use in the sequel. So from now on, I will only talk about computation of Grobner basis in terms of convergent linear rewriting system. Before going into non-symmetric operads, let me talk a bit about linear rewriting. So rewriting in linear context appeared a lot in many settings in computer science, especially with works working on term rewriting system, modulo, associativity and commutativity theories. But it also appeared a lot in algebra, in algebraic contexts. So for instance, here I give a few examples. So linear rewriting was studied for commutative algebra with works of Janet, Bourberger, and so on. It was then studied for associative algebras with works of Bockut, Bergman with the Bergman-Diamond lemma, for instance, and Mora. And more recently, it was extended to higher structures, and in particular operads, with, for instance, works of Dodsenko, Koroshkin, and Malbosren very recently. And actually, since the introduction of the Grobner basis theory, Bourberger gave an algorithm to compute a Grobner basis, and this algorithm is in some way similar to the Knut-Bendix completion procedure. That is, one considers a critical branching, try to see if it is confluent. If it is confluent, you leave it, you forget it. And if it is not, you just add another rule that is oriented with respect to the monomial order that we have, and to make it confluent, and then try to study the new critical branchings or critical pairs that are given by this new rule. And actually, since these pioneer works, there were a lot of improvements to the procedure of completion of Grobner basis. And for instance, here I gave two examples. So in 1971, Bourberger gave a criterion based on CZGs, that are relation among relation, to remove some critical branchings that are non-necessary. And then what we'll talk about today, Fogère in 1999 and 2002 gave two algorithms that improve this procedure in the sense that we do not only consider one critical branching at each step, but we can parallelize the computation by allowing to complete a subset of the critical branching at the same time. And that's what Isaac will talk about later. And these procedures to improve the completion of linear rewriting system are mainly based on two principles. The first one is to first eliminate the branchings that are non-necessary in order to have a confluent rewriting system. And for instance, we can think of the orthogonal branchings that are branchings on some terms that do not overlap. And since these are confluent, we do not need to consider them when we choose when we do a completion procedure. And the second one is so you have the critical branchings and you have to complete them to make them confluent, but some of them may not be necessary to be checked. And these are what we call redundant critical branchings, and one can try to remove redundant critical branchings using CZGs. That is, if you have a critical branching that can be obtained from other branching and its confluence is ensured by confluence of other branchings, you may not want to consider it as well. And so these were studied a lot for the case of commutative algebras, but recently it was also extended in the case of non-commutative algebras by works of Xiu, Chenavier, and Hofstadter more recently. So this is known in this context now, but it turns out that in higher dimensions, it is yet to be explored, these computation procedures. And in this talk, the objective is to try to develop an F4 computation procedure à la Fougère for non-symmetric operads. So to do so, let me talk a bit about what is a non-symmetric operad. So a non-symmetric operad is a collection of vector spaces P of k indexed by natural integers in which the vectors of the vector space P of k are called elements of arity k. And we require that this collection of vector spaces is equipped with some partial compositions like this. So that is for any I smaller than m is the first element here, an element of P of m can be I composed with an element of P of n to give an element of P of m plus n minus 1. This is the basic point for the definition, but I will not talk, I will not give much more details about non-symmetric operads here. I will just introduce a way to represent and to figure out what are non-symmetric operad, which is given by trees. So actually, the elements of a non-symmetric operad can be represented by trees as follow. So an element of P of m can be represented by a tree having only one leaf and m outputs, m branches as outputs. And the I composition in that context is given as follows. So you take the second tree, so the tree of P of n, and you juxtapose it on the ith branch of the first tree, which is exactly the result that we obtain on the right here. And this is an element, a tree with m plus n minus 1 outputs. So it corresponds to this composition here. And the set of three monomials like this will be denoted by T of sigma, where sigma is some set of generators that we will use as inner vertices of the trees. You see here, we have trees that are labeled by mu and nu, and we will have a generating set for these labels, and the set of monomials on this label will be denoted like this. And what is important, if we have such a set, a grading set by arity sigma, so in sigma, you may have generators with different arities. So here, mu as arity m, for instance, you may span what we call a free operad. And a free operad is a data on which your elements, so the vector space containing elements of arity k will be obtained by all the trees that one can obtain by composing in various ways the elements of sigma, the generators of sigma. Okay, so we will have rewriting rules on trees. The trees that I described are the elements that we will rewrite on. But in order to define a rewriting system, we need to describe what is a rewriting step. And to do so, as it is usually done in the context of algebraic rewriting, we need to define what is the notion of context. So we will say that a context of arity k is a tree, is a planar tree denoted by C with this box, whose inner vertices are elements of the generating set sigma, plus a formal symbol square underscore k that one can see as a whole in the middle of the tree. And this symbol as an arity k, it's like you have a tree and you put a hole in the middle. And for a tree monomial that has the good arity k, we define the tree monomial C of u by replacing this formal symbol square k with u. So this is exactly this process. We have a tree with a hole, and we just put the sigma, the symbol u, which has the good arity in the middle. And the context will be useful to define rewriting step, but as I also said in the introduction, we need some kind of, we need rewriting systems that are compatible with an order with good properties. So that's what I'm defining now. So this order with good properties is an operatic monomial order, and it is the total order on planar trees such that for all three monomials u prime, v prime, such that u is smaller than u prime, v smaller than v prime, then we require that u I composed with u prime is smaller than v I composed with v prime. And if we define things like this, what we need in the sequel is only a monomial order that is compatible with the rewriting rules. indeed, if we have such a monomial order on which we know that the source is always greater than the target, and using these properties of monomial order, we can then compare rewriting rules in context and thus rewriting steps, which is what I will define now. So I mentioned, I defined the free operaid, and now I can define an operatic rewriting system. So an operating system is a data sigma. So sigma is a generating set, graded generating set as above. And R is a binary relation defined like this. So it's a set of relations whose source will be elements of T of sigma. So these elements are three monomials. So we will rewrite a monomial into an element of the free operaid, which is a polynomial. So it will rewrite a monomial into a polynomial, and we consider ORS that are compatible with a monomial order. So that is the source of the rewriting rule will be always greater than any monomial in the target. And if you remind what I talked about in the introduction, it corresponds to the fact that one wants to reduce in some way the leading monomial with respect to the order we fix. And finally, I can define what is a rewriting step. So we will want to consider reductions of the form. We have a monomial C of source of alpha, and we want to apply a rule of R here inside this monomial, but with a linear part. And the linear part is given by, you may add a scalar on the left of this monomial, and you may add a linear polynomial. And such a reduction will be called a rewriting monomial if there is no linear part, that is the scalar lambda is equal to 1 and the polynomial g equals 0. We only reduce the monomial here. And it is moreover what we call a rewriting step if moreover the monomial we rewrite, so C of the source of alpha, does not appear as a monomial in the polynomial g. And I will not explain too much why here, but this is mainly because we don't if we don't do this, we may have some trivial non-termination issues. And finally, now that we define this, the data of the elements of the free operaid together with these rewriting steps define an abstract rewriting system, which is terminating by the assumption we put on the monomial order. And now what we want to talk about is the confluence of this operatic rewriting system. So to talk about confluence, we need to introduce a branching, which is a pair of rewriting paths with the same source, with the same tree as a source. And a local branching is a pair of rewriting steps. And in that context, local branching can be separated into these four families. So additive, that are rewriting on two distinct monomials inside a polynomial. Multiplicative, that are rewriting on a given monomial, but at two places that do not overlap. Intersecting, which is this time rewriting on a monomial, but at two places that overlap. And finally, critical, that are rewriting on a monomial, which is minimal in the sense that there is no part of the tree that is not rewritten at all. So it is minimal by context in some sense. And we have the following results. So the first one is well known. The critical branching lemma states that an operatic rewriting system terminating or compatible with that monomial order is locally confluent, if and only if it's critical branching or confluent. But one can also do better in that context with essential branchings that were introduced by Malbos and Rennes in 2021, that are atomic critical branching in the sense that these are particular critical branchings in which a third critical branching cannot appear. So I will not give more details about that now, but we could discuss this at the end of the talk if you wish so. And Malbos and Rennes prove in 2021, for instance, that an ORS terminating is locally confluent if and only if its essential branching are confluent. And this will be used in the sequel of the talk by Isaac to ensure as the starting point, for the F4 completion procedure to discuss the choices that one can make for the completion procedure. So thank you, Isaac. I'll let you talk.
All right, thank you, Benjamin, for the first half. Apparently I can't share my camera. Someone prevented me from sharing my camera. Am I still here? Hello?
Yes, we can hear you.
Okay. Please go on, we can hear you.
Okay, well, pick up where Benjamin left off. So as announced, we've given a presentation of an operaid. We want to calculate a Grobner basis using completion. So this is a relatively well-known procedure. I put here an algorithm just to describe the general idea. We start with a set of rules of a terminating rewriting system, and we want to get a confluent rewriting system. And to do this, we look at all the critical branchings, and taking subsets, we add rules to make branchings confluent. We check if there are new critical branchings. And at some point, if the set of critical branchings of non-confluent critical branchings is empty, then we have a confluent rewriting system. And in our work, we look at 2 points where we try to optimize. So first, instead of taking critical branchings, we will look at any confluence obstruction map. So this is something I will define. And then the other part, which is the part related to Fougère, when we choose a non-singleton subset of branchings, we can look at parallel completion in order to complete multiple branchings at the same time. First, I will talk about confluence obstruction. The idea is that we want a map that to a rewriting system associates a set of branchings such that if these branchings are confluent, then the entire rewriting system is confluent. So more formally, we call this map CO. Then we want this property that X is CO of X confluent if and only if X is confluent. This is a very abstract notion, but it's the notion that is sufficient to have a completion procedure. And in practice, a good heuristic is to take a confluence generating set, which I'll define just after, but before I just want to say that critical branchings form a confluence generating set. And the fact that the critical branchings form a confluence obstruction map is exactly the critical branching lemma. So a confluence generating set is a set of branchings such that any other branching of X can be factorized into branchings F1G1 to FNGN, which are either additive, multiplicative, or in this set B. And so some details, F starts with C1 bracket F1, and then it is extended by some rewriting path F prime, and G is Cn bracket Gn with some G prime, and for each I, we have Ci bracket Gi, which is equal to Ci plus 1 bracket Fi plus 1. And as Benjamin said, the essential branchings also form a confluence generating set, and so therefore a confluence obstruction map. And this is what we will be considering in our completion procedure. The second point was parallel completion. So this is introduced by Fougère in 1999, not 1995, called F4. And so here, so he introduced it for polynomial rings, and here we will describe it for operads, non-symmetric operads. So in order to calculate things in parallel, we need a subset of branchings B. And so this is selected using some selection strategy. The next step is to get the list of all rewriting monomials that are involved in the reduction of these branchings. So each branching, we try to reduce it to normal forms. And every time we reduce, we're applying some rule in context. So this is a rewriting monomial. And so this is what we add to R prime. Then we construct a matrix MR prime, whose rows are the elements of R prime, and whose columns are the monomials, so just trees, that appear in T at some point. And so in this way, we can represent each row, each element of R prime as a row with coefficients corresponding to the coefficients of the monomials in T that appear in this rewriting monomial, either in the source or the target. This is just one sentence, but I have an example later, which I hope I'll have the time to present. That should make things clearer. And then here's where Gaussian elimination comes in, as announced in the title. We reduce MR prime to its row echelon form. And the rows whose leading monomials are not the leading monomials of rewriting rules in R prime are now new rules that we add to R prime. So this is where we add our rules to make these branchings confluent. in summary, we have parametrized our completion procedure by a confluence obstruction map and a selection strategy S, and we have a concrete way of parallelizing completion. So instead of critical branchings, we now have a CO, and we select our branchings using a selection strategy. To end, I'm going to briefly go over a case study, which is we will consider the anti-associative operad. So consider the following ORS with one generator X of arity2 and one rewriting rule F, which rewrites this X on the left to the X on the right with a minus sign. So if X is seen as a multiplication, this is almost like associativity. Multiplying on the left, then on the right is the same as multiplying on the right, then the left, except we have a minus sign that appears. And we'll now execute the completion procedure with the confluence obstruction map that selects essential branchings, the selection strategy that selects branchings of lowest weight, path lexicographic order, and there's also reduction strategy that needs to be specified, which I take from a work with Philippe Malbos, but this isn't very important, so I won't go into details. And so let us start. So the first step is to construct our essential branchings. And at first we only have one, which I've written inline to save space. But the idea is that we have a branching that on this tree monomial here with 3 x's, which we rewrite either to the second one or the third monomial. Following, if we rewrite f on the top, we apply f on the top or on the bottom. From these two monomials, we can continue to reduce these, and so we get these, the fourth and fifth monomials, and all of the rules that we have applied in context are here on the side. So these are the rows, this is R prime, and then here are the monomials that appear in T, and we get this matrix. If we apply row reduction, we get ones on the diagonal, and I've put these monomials in order. So the greatest monomial is the leftmost. And so since I have ones on the diagonal, that means I have a rewriting rule with leading monomial each of the monomials of these columns. And it turns out that only this last one is a monomial that is not the leading monomial of a rewriting monomial. And so we add a new rule, and this is how we complete to make this first branching confluent. And now we have to check once again that we have, if we have confluence, and we do not, we actually have 5 essential branchings, and we have 1 critical non-essential branching, which I have not drawn. And this one I'll detail even less, but we have a matrix with quite a few monomials and quite a few rewriting monomials. And actually every single monomial that appears here is the leading monomial of a rewriting monomial in R prime. And this means that our criteria for adding new rules picks up no new rules, because it's impossible to have a rewriting rule whose leading monomial is not the leading monomial of a rewriting monomial. So this is, I don't know if it's better written down. There are no new rewriting rules, so the procedure terminates. And our final convergent presentation has this, the original rewriting rule, and we add one that rewrites this tree with 3 inner vertices to 0. In conclusion, we have improved the completion procedure for non-symmetric operads in 2 ways: by reducing the number of branchings, so by considering essential branchings, and by parallelizing the procedure following Fauger's approach. We've also identified this notion of confluence obstruction map, which can be used, we can replace it with any better choice if we find such a choice. Another outlook is to apply this completion procedure to other monoidal structures, or structures that have this sort of rewriting possibility in higher dimensions, such as properads. And finally, we can interpret this completion procedure modulo the linear structure. This is something that Benjamin is more familiar with. That concludes the talk. So thank you for listening to us. If there are any questions.
Thank you very much. So let's see if someone have a question or a remark or comment. So in the meantime, I do have a question. So can you quantify in some way how much more efficient is this parallel procedure compared to traditional completion procedure? I mean, maybe either in practice or like a complexity result or something which would help us understand how much better it is.
I'm not too familiar with the practical efficiency. From what I understand, for polynomial rings, it is more efficient. I don't think there are any complexity results, but
but is it like a magnitude, an order of magnitude faster than the naive approach, or is it just a small improvement which is already good?
Unfortunately, I do not have the answer to that question.
Okay. And also, so I see that Vincent is asking on the chat whether there is an online implementation, an implementation available online somewhere.
We do not have an implementation, mostly.
But I think, yeah, for some work on Opera, there is an implementation for computing Gromov bases that was done by Dotsenko and Koroshkin, no?
Yeah, by Dotsenko and one of his students.
Okay. And about the complexity, so yeah, I don't know if there are any complexity results, but yeah, for sure, we found some references where they were doing the two completions procedure in parallel, and it was, yeah, more efficient for sure when you try to, when you have a good way to choose a parallelization for the critical branching, especially in the case of yeah, homogeneous presentation and this kind of stuff, because you can select all the critical branching with the same weight in some way.
Okay. So is there any other question? So maybe I do have one last question. So this work was originally done for associative algebras, and then you generalize this to operads, and then you mentioned properads. So how much work is it when you go from one setting to the other? And do you think there could be some kind of abstract approach where you could do all this once for all, and then you just change the notion of context or the notion of algebraic structure or something like this? But could this be done in a very general way?
I guess I can answer. So this is a hope to have a very general approach. The problem is that oftentimes the general type of structure does not have a notion of monomial, which I think is very important in order to do rewriting. And so one difficulty is defining a general context where there are monomials. Okay. But once that is done, the next challenge is seeing if there are different types of branchings and what type of minimal set of branchings we can get. Because, for example, essential branchings already more complicated, so we haven't defined them, but are more complicated in the context of operads than for algebras.
Yeah. Okay, so thank you very much.